Today we discuss inverse function theorem, one of the important and crucial theorem familiar to all, and obviously we also discuss this theorem now, and this one is that means basic theorem for analysis and calculus also. We also start with this theorem, and this theorem also led many innovations in this part. So we write now this theorem. Let omega be a subset of Rn and let f omega to Rm be a function such that f is continuously differentiable on omega, and there exists a point c belongs to omega such that f dash c is invertible. Okay, then then first one we write here. Then first one, there exists an open set U. There exists an open set U in Rn precisely in omega. Precisely in omega, with C belongs to U. With C belongs to U, and an open set and an open set V in Rm with Fc belongs to V, with Fc belongs to V, such that F is 1 on U, with Fu equal to V. Okay, then next we write here F inverse is differentiable at Y. F inverse is differentiable at Y with F inverse dash Y equal to F dash X whole inverse with Y equal to Fx. Now we're going to prove of this theorem. Okay, we just write here. Now we're going to prove of this theorem. Now write A equal to F dash C and note that A is invertible. Okay, then what we get, then A inverse norm equal to 1 by norm of A. Okay, A inverse norm equal to 1 by norm of A. Okay, next we talk about now, let alpha belongs to 0 1 open and epsilon equal to alpha norm of A. Okay, marked as 1. Now we erase the above portion and going to further discussion of that. Okay, then we known about it, since f dash is continuous, at C, then what happened, then there exists delta C epsilon greater than 0, delta depend on C epsilon greater than 0, such that norm of f dash x difference f dash c is less than epsilon for all x belongs to omega, with norm of x difference c less than delta. Okay, then we have an open wall, then we have an open wall. Oh, there is again problem create. Why this problem create, I don't know. There is some typical lower thinking persons are here who disturbed in this way. But now this one is clear. I also going to further proceed. Then we have an open wall B delta C, okay, in omega, set u equal to B delta C, okay, and V equal to f of u. Note that U is a open set in Rn. Note that U is an open set in Rn and Y belongs to Rm. Y belongs to Rm. So define phi omega to Rn by phi x equal to x difference A inverse fx difference y for all x belongs to omega. Okay. Now note that phi is differentiable. Phi is differentiable with phi dash x equal to is that lower portion, and going to further discussion of that, with phi dash x equal to how much I difference or 1 difference A inverse fx f dash x, okay, for all x belongs to this omega. Then norm of phi dash x equal to norm of I difference A inverse f dash x, okay. Then what happened? Then this one equal to norm of A inverse A difference A inverse f dash x, okay. This equal to norm of A inverse common A difference f dash x. This less than equal to norm of A inverse norm of A difference f dash x. This less than equal to norm of A inverse and norm of f dash c difference f dash x. This less than 1 by norm A epsilon. This equal to alpha by 1. Hence by MVT, hence by mean value theorem, we get norm of phi x difference phi y less than equal to alpha norm of x difference y. for all xy belongs to this omega. Okay, now here write, so phi omega to Rn, so phi omega to Rn be a contraction on omega, and hence on omega phi u to Rn is a contraction. So it is that portion. So phi hence on u phi u to Rn phi u to Rm phi u to Rn defined on this is a contraction. Okay, is a contraction, and we now show that phi is a contraction from u to itself. Okay, phi is a contraction on u to itself. Okay, now how we proceed? We proceed in this way. Let y0 belongs to v with f of x0 equal to y0 for some x0 belongs to u. Since x0 is an interior point of u, then we can find a open wall Brx0 on u with radius r so small such that Brx0 subset of u for x belongs to Brx0. Here we write phi x difference x0 equal to here norm phi x difference phi of x0 plus phi of x0 difference x0. Okay, now norm of phi x difference x0 less than equal to norm of phi x difference phi x0 here plus norm of phi x0 difference x0. Okay, less than equal to alpha norm of x difference x0 plus norm of phi x0 difference x0 less than equal to alpha dot r plus norm of phi x0 difference x0. This marked as 2. Now let y belongs to Br1 y0 here phi x equal to x difference f of, sorry, x difference, not here, a inverse of fx difference y. Okay, so phi x0 equal to x0 difference a inverse of f of x0 difference y. Okay, now we write here, so norm of phi x0 difference x0 equal to, here difference a inverse of f of x0 difference y. This equal to norm of a inverse f of x0 difference y. Okay, then we write here, this one equal to norm of a inverse of y0 difference y. We now erase our portions and going to further discussions of that. Okay, so we erase here. Okay, now this one less than equal to norm of a inverse y difference y0. Okay, norm of this one less than equal to 1 by norm a, and this one is we marked as r1. So this r1 equal to, we write it, r1 equal to norm of y difference y0, and now we marked it 1 by norm a. Here r1 equal to 1 minus alpha r. Okay, this total equal to, we mark it 1 minus alpha r. Okay, then what we get, then r1 equal to 1 minus alpha norm a norm and r. This one, where r1 equal to, where r1 equal to 1 minus alpha r norm of a. This one less than equal to this multiplied by this, so equal to r for all x belongs to brx0. Okay, this implies that phi x belongs to brx0. Okay, subset of this one. So we also going to this form, that means conclusion that phi x belongs to brx0 where x0 is open. Now we going to another step. Okay, we erase lower portion and going to another step. Hence thus y belongs to br1 y0. Okay, y belongs to, then what, br1 y0 open wall. Then the mapping phi from brx0 to br open x0, define phi defined by what? Defined by phi x equal to x difference A inverse fx difference y. X belongs to B or x0 is a contradiction. Okay, is a contradiction. Hence, by Banach contraction theorem, hence by Banach contraction theorem, phi has a unique fixed point. Phi has a unique fixed point. That is the equation fx. That is the equation fx equal to y has a unique solution. Has a unique solution. Hence, f is 1 on u. Hence, f is 1 on u. And on 2 also. And on 2 also. Since functions, since u is finite, that means finite dimension Rn to Rm. So Rn is finite. Since Rn be finite dimension. So on to so we get fu equal to v. Okay. Now we're going to second proof of this theorem. Here what we do in first proof, we do just we write first in first step we set something a equal to f dash c and then going to discussion about that. And in first step we write just f dash is continuous, and then we in second step we define phi x and obviously see that phi is contraction, and in third step we also see phi contraction from u to itself. Then in fourth step we see that norm of phi x difference x0 less than equal to 1 minus alpha r. Not phi x difference x0 less than equal to r. Less than r. This one is divided by in two parts. That means this one we divide phi x difference phi x0 and phi x0 difference x0. Then phi x0 difference x0 is less than 1 minus alpha r, and phi x difference phi x0 is less than alpha r. So this one is phi x difference x0 norm is less than r. So phi x belongs to open ball br x0. Then y belongs to br1 y0. Then the mapping phi from br closed x0 to br open x0 defined by phi x equal to x difference a inverse fx minus y is a contraction. Okay, by Banach contraction theorem, phi has a unique fixed point, so the equation fx equal to y has a unique solution. Hence, f is 1 on u and on 2. Since Rn is finite dimension, so fu equal to r. Fu equal to v because on 2. Now we're going to this second part, or the proof of this second portion. We erase that portion and going to discussion about that. Okay. So we write now here let y and y plus k be to be two numbers or members. Okay, two members, not here, two members of p. Then there exist x and x plus h belongs to u, such that f(x) equal to y and f of x plus h equal to y plus k. Okay, hk not equal to 0. By Banach lemma, we get f inverse f dash whole inverse exists. Since f is 1 1 and on 2, that means bijective, and then f inverse is exists. Okay, but here by that means we write that means by Banach lemma f inverse test is exists. Since f inverse is, that means f is continuously differentiable, so f dash c is invertible, so f dash x whole inverse exists. Okay, now we also going to this. Here we write norm of f inverse y plus k difference f inverse y difference bk by norm of k. Okay, then this one equal to how much we write x plus h difference x difference bk divided by norm k equal to norm of h difference bk by divided by norm k. This one norm of h difference f dash whole x inverse k by norm k. This one equal to, here we write f dash x whole inverse k difference h divided by norm k. Okay, now we write here equal to f dash x whole inverse k difference f dash x whole inverse f dash x h norm of this by norm of k less than equal to norm of f dash x whole inverse equal to norm of k difference f dash x h divided by norm of k. This one equal to f dash x whole inverse, here k equal to f of x plus h difference f of x difference f dash x h by divided by norm of k. This one equal to, here we write norm of f dash x whole inverse equal to norm of x plus h difference fx difference f dash x h by norm of h, here norm of H by norm of K. We marked as 3. Okay, we marked as this one is 3. Then we're going to further discussion of that. We erase that portion. Okay, now we write here, note that, okay, norm of phi of x plus h difference phi x equal to norm of x plus h difference A inverse of f of x plus h difference y difference x, here a this one in bracket, then this one is better, x difference A inverse f of x difference y. Okay, norm of this equal to norm of A inverse f of x plus h difference f of x difference h equal to norm of A inverse f of x plus h difference f of x difference h equal to norm of h difference A inverse k. Now note that norm of h difference norm of A inverse k less than equal to norm of h difference A inverse k. This equal to norm of phi x plus h difference phi x. Okay, this less than equal to alpha norm of x plus h difference x equal to alpha norm of h. Then norm of h multiplied by 1 minus alpha less than equal to norm of A inverse k. Okay, then this implies that norm of h divided by norm of k 1 minus alpha less than equal to norm of A inverse. Okay, now we erase the third portion and going to further discussions of that. I think all are understand this portion. Okay, this implies that norm of h by norm of k less than equal to norm of A inverse by 1 minus alpha. So h tending to 0 as k tending to 0. Okay, we get now we get norm of f inverse y plus k difference f inverse y difference f dash x whole inverse k norm of this by norm of k less than equal to norm of f dash x whole inverse equal to f of x plus h difference fx difference f dash x h divided by norm of h. Here norm of h by norm of k. Okay, this equal to norm of f dash x whole inverse hence. So what we get here, we get just tends to 0. Okay, we get this tends to 0 and as k tends to 0. Okay, since f is differentiable and f inverse f dash whole inverse exists, then not a problem. And here norm of h by norm of k equal to as k tends to 0 and h tends to 0. So f inverse dash is differentiable at y. Okay, because this is tends to 0, this whole term tends to 0. Okay, as k tends to 0. So f inverse is differentiable, okay, at y with f inverse dash y equal to f dash x whole inverse with y equal to fx. So we also discuss second part also. Here we write y and yk from V, and then there exist x and x plus h belongs to u such that fx equal to y and f of x plus h equal to y plus k. Then Banach-Lemma f inverse f dash inverse exists. Okay, so f inverse y plus k and f inverse y difference b equal to this one b k. Okay, equal to x plus h difference x bk, and we also calculate this. That means we write here b equal to f dash x whole inverse. Okay, so we calculate here and going to that norm of f dash x whole inverse norm of x plus h fx plus h difference fx difference f dash x h no, by norm of h multiplied by norm h by norm k. So now we note from note we see about that phi x plus h difference phi x less equal to norm h difference a inverse k, and norm is difference norm of A inverse K less than equal to, here we write alpha norm of H. So norm of H by norm of K equal less than equal to norm of A inverse by 1 minus alpha. Hence from 3 we get this one less than equal to this one, and norm of H by norm of K less than equal to this A inverse. Okay, A inverse 1 minus alpha. So what we get from here, we get from here this one tends to 0 as K tends to 0. Okay. Yeah. Since f dash x is differentiable, okay, then this one is f inverse is differentiable at y with f inverse dash y equal to, here b equal to f dash x whole inverse. Okay, so we here we stop now.